We have Ben Titzer, another co-creator of WebAssembly, who's going to be talking about WALI, the WebAssembly Linux Interface. Once I get this working.
Can I have that microphone? I might wander around.
Oh yeah, go for it. Just be careful speaking into both at once. Might cause some problems.
All right, thank you. So I'm going to talk about some work that we've been doing recently on the WebAssembly Linux Interface, or WALI.
If you do want to, you've got to.
Okay, I'm going to try to. I got to figure out some strategy here. So we're going for pronunciation WALI and not like WALI or WOLI or anything. There's some difference in pronunciation, WASM, WASM, and things like that. We're going with WALI. I'm just decreeing that. So the PhD student here, Arjun Ramesh, super hacker of the highest order, implemented all of this. And another student, Tian Xu, has also worked on this too. And the faculty member that I've been collaborating with is Anthony Rowe. He's in the ECU department at CMU. So I am trying to motivate people to think about WebAssembly as the universal execution format of the future. So my quote goes something like this: I know that Unicode can trigger people because Unicode has got a lot of weird things in it, but just think of this as an analogy that fits in the advantages and not the disadvantages. So WebAssembly will be like Unicode. All the previous character encodings that people had before Unicode, they were all eventually discarded, and we moved forward with one standard. So WebAssembly is going to be that for executable code. So if we look at the core strengths of WebAssembly, Andreas likes to use the term a portable abstraction over hardware, so the instruction set architecture, and that's what WebAssembly, core WebAssembly gives you. It's an open standard, which is great. Anyone can implement it, anyone can use it. It gives you close to native performance, so you can compile low-level languages and low-level code and run pretty close to what you would get on the CPU, and of course, it's language agnostic. It's well specified thanks to efforts of people in the room. It's been formalized and machine checked, so we're pretty sure that this is right. So we've got a level of rigor that's unheard of in the software world. And there are many engines out there. So different domains, including the web, including cloud, and embedded systems have engines now available. There are many application domains for WebAssembly. Eventually, any place where you'd want to run code, I think that you should have WebAssembly as the format for running that code. So obviously it was born in the web, so there's web applications and libraries. Cloud and edge systems have started to appear, so there's many different cloud platforms and edge platforms and many proposed academic systems, and it seems to be that WebAssembly is emerging as the standard for accepting applications to run, which is great. It's also a subject of PL and VM research. There's probably close to 200 or 300 papers now that use WebAssembly. People have been thinking about the Internet of Things, and I'm not talking about necessarily washing machines, but I'm talking about like medical devices, like something that you would use in a hospital. Those kinds of things, actually, maybe WebAssembly is the executable format that they use for exchanging code. We talked to some industry partners, and so for example, Siemens, the name of this room, is one of the partners in the research center, and they do critical infrastructure stuff. So think about things in power switching grids, things in, I don't know, nuclear power plants and stuff like that. What code do they run? They want to have some systems that actually have some security guarantees. So maybe there's an application domain there. So under this concept of cyber physical systems, so computers interacting with the physical world, so maybe critical infrastructure is somewhat under that, but also things like factory automation, so robots that build cars and build other things, they run code, and those are embedded systems that have been developed since the 80s and 90s, and those are starting to upgrade into the modern world. That also is related to real-time distributed systems. So for example, if you think about a robot that's building a car or building, I don't know, whatever item that you think is interesting, like a guitar, there's robots that build guitars. The control loop, part of that can be run on the actual robot, on the device, and maybe some of it can be run on some software which is located in the factory, so like a mini cloud or like a mini edge system right there. And so that's all real-time distributed control. Augmented reality, virtual reality, these things are all taking off. So the issue is that there's not been a lot of WASM adoption here. People have written papers about this, people have experimented with it, but there's not really like production systems that are using WASM quite yet. And partly it's because there's not a lot of interfaces yet, and the existing software stacks that they have, there's been a lot of investment. So Siemens, for example, might have 100 million lines of code. I just made that number up. That's not, they didn't give me any information on that. But they have like millions of lines of code, and of course they're robots. They're not gonna rewrite them in, I don't know, Ruby, just on a whim. They want to reuse that investment. And of course they have stability requirements too. So when they have a deployment into a factory, this robot system might work for 10 or 20 years. And so they want to be able to have some guarantee that their software is going to keep working in that time frame. So why do we want to build a WebAssembly Linux interface? So this is a picture of Mount Everest. And so, because it's there, right? And that quote actually comes from George Mallory. He was one of the first people to try to summit Mount Everest. He did not succeed. He died in 1924, so 100 years ago. And he was actually very close to the summit. But they found his body in 1999. So maybe don't use this entire analogy. But why are we building a system called interface? And I would say that it's basically inevitable. If you look here, so the system software is down there. It's inevitable. It's the lowest level of abstraction in user space. We've been doing that for half a century. It's pervasive. Basically, every software system is going to have a bottom layer, which has some user space. So there's no way of getting around it, and it's everywhere. It's typically very stable, too. So, system call interface, since everything is built on top of it, it can't really evolve at the same speed as application layer APIs. And also, system call interfaces are designed to be the minimal overhead. So they try to do zero copy as much as possible, and they try to be as close as possible to the performance that you could get if it wasn't there at all. Another great thing is that they're kind of done. They're already specified. There's not a lot of design problems to solve there. Things are already built on top of them, and so they have already solved the problems that they have set out for. Of course, you might talk it to someone who works in operating systems and say, no, they're not done, and we're doing new things. And that's true, so there's like new kinds of async I/O interfaces and things like that. But relatively speaking to the kinds of evolution that we see at application layer, these are effectively done. Why did we pick Linux? For the same reason that we pick WebAssembly. It's an open platform. It's pervasive on so many devices. There's probably 100 billion devices in the world that actually run Linux. It's stable too, and it's more stable than most operating systems. So in particular, Linus Torvalds himself has the quote that don't break user space. So the actual ABI for the kernel is so stable that you can take a binary from 1995 and it will run on today's Linux if it's the same CPU. This is also proof of concept. So this is an academic project. We're just building one example to see if this can work. It's good to pick an example that has a wide adoption already. It may be the case that other operating system interfaces follow, so I'm not going to posit that Linux is going to take over the world and everybody must run Linux. And of course, all the WASM engines, or nearly all the WASM engines today, they already run on Linux, mostly because they are written in C or Rust or another language which runs on Linux. So what is it? We're talking about a low-level WASM API. So it's a set of imported functions. It could hopefully fit in the component model in the future. It mostly maps one-to-one with Linux system calls as they are today. And we've done this in a way that preserves the in-memory isolation properties of WASM. So nothing about the system call interface opens you up to some kind of memory vulnerability. So you can use it just like any other WASM API and communicate through linear memory. Key thing is it's not an application sandbox. We are not trying to sandbox the file system or devices or resources or network. When you're running against the WebAssembly Linux interface, you have the same privileges as a native process. And so that means that we're not thinking that you're going to take random code from the internet, which is compiled against the WebAssembly Linux interface, and just run it. That would be a bad idea, because a WALI program is effectively a native program. So it has all the privileges of a native process do. There is a little bit more than just being a native Linux program, though, of course. You get additional security guarantees. In particular, since WASM is a memory-safe executable platform, you cannot inject code into a WebAssembly program. Like you can't overwrite some buffer and overwrite the stack, right? So a Linux program here that's compiled against WALI is going to be, just by design, safe from any remote code injection attack. The great thing is that since we've designed it as a one-to-one mapping, it is really easy to implement. In fact, it's mostly just a forwarding from the application to the kernel. Like you almost have no adaptation whatsoever. So it's a pass-through implementation. The entire implementation, we chose to implement it in the WebAssembly micro runtime, 2,000 lines of code. And probably 3/4 of that is just like line by line, many system calls that go directly through. And so the idea is that eventually we will allow WASI APIs to be built in WASM, so their implementation won't be built inside the engine, because WASM will have the capabilities of expressing the low-level things that you need to do to implement WASI. And the idea there is that even though WebAssembly itself gets more capabilities and you can do more things that are potentially more dangerous, the overall system architecture allows us to introduce a layer. And it allows us to run WASM on whole new domains that doesn't run yet. Okay, so this is a bit of an OS review. I'm just going to kind of make it a little bit more clear what I'm talking about. The way native applications run is that obviously there's this process abstraction here, which is we have some layers here. They cannot invoke the privilege instructions. So when you're running on the CPU, you can only kind of access the things that are in your memory space. The operating system is what gives you the capability to do anything outside of your sort of own little memory space. It's very analogous to WASM, and that's the system calls at the bottom. And that's also the way you communicate with other processes through the API. So on x86-64, it's the syscall instruction. And it's literally like you put the arguments in the registers that you want, and then you invoke the system call instruction, and you go directly into the kernel. And obviously different kernels, they have different system call interfaces, they have different memory layouts, they have different process abstractions and capabilities that they give you, but they all go through the same mechanism at the bottom. And Linux is a Unix, and it's inspired by Unix. It does not implement POSIX exactly how POSIX is specified, so any difference between what POSIX specifies how the semantics of something like shared memory works, that can be papered over by libc. So there's some software at the bottom, which is actually in your executable, which you link against. So one of the first things that we looked at is, actually, this seems like a crazy idea. It seems also like a gargantuan amount of work. It's actually not. It turns out that most applications don't use the entire system call set. There's about 500 system calls on Linux, and if we look at these various things like bash, so that's the actual shell here, memcached and SQLite, they actually, between the three of them together, and this is actually their dynamic frequency, you can see that it's like very much like a power law. They don't use a lot. They don't use the entire system call set. Only about 130 covered all the ones here, and we're able to run many things just with that set. That's less than a third of the overall set. And again, I mentioned before, most of them are just passed through, so they're simple implementation. And that means that it's not like a big burden to implement these system calls. Another question is, isn't Linux portable across lots of CPUs and systems? Is it like totally different? Are the system calls totally different? And actually, it's not the case. So of the 500, this is actually 500 total over all the ISAs. Actually, most ISAs are more around 300, and there's like this core set, which is common. So across, that's ARM64 and RISC-V 64 and x86 64. There's basically this green set, which is the same. And the yellow, and we actually looked at, there's probably 24 or so Linux ISAs that are supported in the kernel source tree. The ones that are really weird are some porting of something like maybe AIX. So IBM did a lot of work to develop portability for AIX applications onto Linux. And so they would introduce like maybe 50 calls which were AIX specific so they could get their applications running. And so maybe on S390 there's a bit more. But typically like the core set here is actually very common. And the small differences here, like between ARM64 and RISC-V, like RISC-V is effectively just they took ARM64 and they added or removed a couple. And it's like combining a few things that are like similar but minor differences. So it's not a big difference. So we can categorize the functionality that's in the system calls, at least the ones that we targeted for WALI. About 40 of them fall into the category of dealing with files, dealing with I/O, and so it's the normal things that you think of: opening paths and reading and writing from from file descriptors and stuff like that. But it's also stuff like statting files or doing I/O control and things like that. So those are like the long tail of things that applications actually do, or at least libraries actually use. But if you don't have those, then these applications don't work right. And thankfully, there's not too many of them. Also, you can manipulate the process's memory address space. So you can protect different regions, you can map different regions. There's actually only a couple of calls there, so mmap in particular. There's lots of flags and things that you can use to mmap and lots of different things you can do with mmap. But we mostly are allowing you to do that in a sandbox way. I'll show that in a minute. And so actually it doesn't take that much additional work. Signals are important because that's an inter-process communication mechanism. There's only like 5 calls. Those are the complicated ones of dealing with signal handlers. We'll talk about that in a minute. But also manipulating scheduling, that happens too. Timers for all kinds of things. And then process control. So we're able to run bash on top of WALI. And so bash is a shell that runs all kinds of different processes. So talking about child and parent processes and sending signals and things like that, there are about 20 calls there. Sockets work, mutexes work too. And then on top of the system call, sort of just listing all the things that you need to do, there's a kind of basic things that are assumed in the Unix process model, like you get arguments and environment, and then you have to deal with threads. So our thread implementation is based on how WASI threads work. And so when we map that onto WASM, it means for now an instance per thread. We basically made no modifications to the tool chain. We just reuse what is built into the WASI SDK for threads. And then we can talk about the process model. So WALI applications are effectively going to be a WASM memory with some additional system calls. Well, these processes actually have identifiers. When you're talking to Unix, the PID is really important. You're talking about other processes, those processes' PIDs are important. And like WASM has this superpower where you can locate many processes in the same one. We chose a simple model where the WALI process literally is a native process. So you have a WASM engine, and that WASM engine's PID is your PID. And so you run as if you're sort of that native process. And then for mapping, we have to talk about what does it mean to have shared memory. And we came up with a shared memory model that kind of makes sense. So Luke talked a lot about the component model and mentioned WASI. So WASI is this collection of APIs which are high level and going to be portable. WALI, you can think of it as a complementary interface to WASI. So if we were looking at, before WALI existed, we had this kind of setup here where you think about a WASI application and it's compiled against WASI APIs. The WASM engine needs to implement at least some of those WASI APIs. Some of them can live compiled into your application and integrated through components. But ultimately, the things that need privilege, the things that talk to the actual operating system, are going to be implemented in the engine. With WALI in the picture, now we actually can move some of that up. So in addition to being able to run unmodified applications that run directly on the engine and use WALI APIs, we can implement that stuff that was previously needed to be privileged and be in the engine, can move up into a library that instead uses WALI. And so then the same unmodified WASI application can just move over and it doesn't actually see the layers underneath. This happens to be then WASM. And so we'll get some security benefits from that, which we'll see in a minute. Okay, so obviously when you interact with the kernel has got lots of different things that have to deal with memory. So when you're talking about system calls, many of them take like individual scalar arguments, which are just integers. That's no problem. There's no safety issue there. But some of them take structures and various other things. So if you think about like stat, you pass it a data structure which has got like a C struct definition in the man page. Actually, we need to do a copy in and out because we don't want the WASM application to be able to talk about the process memory. And that's actually pretty easy to do. There's effectively a small address translation. So if you're calling one of these Linux system calls that takes anything to do with memory, we'll do a bounds check and make sure that the WASM application's memory is what we pass to the kernel. So that means, for example, like copying the structs. In particular, we had to define one particular ABI for structs, so it's effectively a 32-bit. It looks like a 32-bit system call API from the WASM point of view, but underneath, of course, your kernel might be 64-bit, so you have to copy and adapt them. But the great thing is that we don't do any copying on I/O buffers. So if you do a read or write call and you pass the kernel like a megabyte, you just have to do a bounds check to the WASM memory and then you drop right into the kernel. So there's a constant overhead and it's pretty small. So you can do high performance I/O, no problem. And so of course, that's so that even though you have these now kernel system call superpowers, you can't actually break the WASM sandboxing model, right? So you don't actually get to see the whole process that you're in. You see this sort of like this virtualized WASM process. And that also means that WALI effectively doesn't need to ever really interpret the arguments to the kernel, because we're not enforcing additional privilege. We really just want to be as thin as possible. It mostly just passes everything to the kernel and just let the kernel do its kernel security thing. And so we have this model where you're effectively the native process. That's not entirely true, though. There are some things that are virtual file systems on Linux that actually do give you superpowers, because the Linux and Unix model is that, yeah, you're a process. You get to do whatever you want with your own memory. There's no such notion of a smaller thing inside of a process. So a thing like procmem, so this is a virtual file system where you can actually do things to your own process memory, that needs to be further sandboxed. So you can't like open up procmem self and then go read what the engine memory is. Signals, this is an inter-process communication mechanism, which is in POSIX. So POSIX has all kinds of standard signals, like what happens if you go out of the bounds of your process memory that's mapped, like SIGBUS, you get a SIG-SEG-V, or if you divide by 0, or other things can happen. So they can happen synchronously and asynchronously. And the way this works in POSIX is that you install signal handlers. So there's a SIG action call. Some of that is in user space, and some of that is in the kernel space. And so we implemented effectively stuff in the engine that needs to deal with signal handlers. In particular, if you set a signal handler for SIG-SEG-V, obviously you're not going to get SIG-SEG-V signals that have to do with engine stuff. You get to service signals that have to do with WASM out-of-bounds memory. So if you access WASM out-of-bounds memory, we'll deliver a SIG-SEG-V to you for your memory, but not for other. And of course, engines might do other things with SIG-SEG-V or SIGBUS. For example, there are engines that implement like orthogonal persistence for memory, and so those kinds of signals, like they basically read only. They map parts of your WASM memory as read only and to detect changes. So you're not going to see those. But there are some important asynchronous signals too. So something like bash, I mean, it has like forks off child processes, and like you can kill those child processes, and you get signals when those child processes do certain things. And so we have asynchronous signal delivery in WALI, and the way that works is there's some polling. So the engine actually, when it compiles WASM code, there's some checks that will insert into the code. Do I need to service an asynchronous signal for this program? If so, then we'll branch into it. And so there's a little bit of overhead there. We actually measure that. I'll show that later. There's some more ugliness with signal handling. Signal handling is one of the ugliest parts of all of Unix, honestly. So you get this ucontext T, which is effectively the machine state when you trapped, for example. We just didn't implement that. You might want to use that if you're doing something super advanced. So I've done plenty with ucontext in my life. So far, we haven't had applications where we need to implement ucontext and give it a machine state. If we want to go further with WALI, we would have to figure out what does ucontext mean in the context of WASM. Is it like your stack frame, operand stack, like frames, all that? So we have to figure out what that means. So far, we didn't have to go there. So there's this thing called the Linux test project, and it is effectively a unit test for the system call interface. And so actually, that was the first thing that we started with, is like, how do we get going? How do we know anything works at all? And so we actually started running the unit tests from this Linux test project. We can now pass most of them. I think it's around 80% of them. And the interesting thing about the Linux test project, it's kind of designed for testing a kernel which is probably broken. And so it forks processes to run like one system call, and then to check whether or not that system call works. It actually sets up a shared memory buffer and uses signals. And so all of that actually kind of has to work. So like the signal stuff and shared memory, all that kind of has to work to even get off the ground. And so the driver of that thing actually has to do some pretty advanced things. And the sort of unit test processes kind of have to work. We actually managed to get all that working so that the whole like test harness runs. And of course, I mentioned bash several times. An interesting thing about bash is that when you build bash, it actually compiles little programs and then runs them to configure itself as part of the build process, which is pretty atypical. It's kind of like got autoconf built into it. And so Arjun, he implemented, so there's a thing in Unix where you can set up a command handler, so for a file type, so you can make a file executable. So he set up a handler for .wasm, which would invoke the engine and run them, and before he had actually tried to do bash. And apparently, since bash does this, it was just trying to run things that it compiled. So it was actually running some WASM code using the engine to get going, and we didn't even realize that until it finished. So it was like just one of these things where, you know, virtualization, just like amazing technology, right? Okay, memory mapping. So this is pretty much the bread and butter of Unix. It's all about virtual memory system and the file cache buffer, all the kernels. So if you read and take operating systems, implementing virtual memory and implementing the file cache, that's like where all the smartness is, right? So this is super optimized. This is designed like back in the day before they had like networks, they had computers that had processes, and the processes would communicate, and so that was where all of the action was in the operating system world. And so this was designed so that you could do all kinds of things without copying. And that's actually really important, not just for having a multi-process architecture on one computer, but also for talking to devices too. So super fast networks like InfiniBand or 100 gigabit Ethernet, and even GPUs, they memory map devices. So in the hardware itself, and the actual memory buses and subsystems and all the cache hierarchy has to deal with that. And so you really want that to work, because if you want to eventually run on these devices and on these machines and do the sort of things that these robots do, it needs to work. It's actually relatively easy to do that in WALI. Obviously, you can't make pages executable, but you can make pages read-only. You can map devices and all that. And since we mostly just pass that down to the kernel and you sort of memory map into the sandbox WASM memory, that pretty much just works. If you memory map something and you want to put it at a specific address, we of course just translate that to the sandbox address and pass it through to the kernel. If you want to map something and you don't care where it goes, normally the kernel would manage that mapping and put it wherever. And so in WALI, we just append that to the end of your WASM memory. So if you just like memory map this thing, we just grow your memory and put it at the end. So that means that there is some state in the engine that manages these maps. So if you unmap them, then we don't shrink the memory, but we do drop that part. So that has to have a little bit of engine support there. So we do allow all this read-only and read-write mappings and manipulating that. Okay, so you need to modify the toolchain in libc a little bit. We started with muscle, so this is also where WASI starts with implementing their libc, and it was a little bit easier to do. So we started with unmodified muscle, and we effectively used the same kind of if-defs in C that you do for like a different Unix, and so it fits in as kind of like just a slightly different Unix. And then all the things that in the tool chain for managing the C ABI and stuff like that, and also for managing threads, we make use of that, so we didn't modify that. And again, like this is specifically because we chose not to try to come up with a different system call set, but have a one-to-one system call set. We could just drop in and everything pretty much just worked. So I call that relatively clean. And so we mostly use stock LLVM. There was some minor changes for this. Okay, so what about the overhead? So the big table here, there's three columns here. One is the overhead for a call, so that's the dynamic overhead. And this is actually includes the overhead of measuring the overhead, so like the actual timer calls and stuff like that. So this is like an overestimate of how many nanoseconds it adds. The floor seems to be around 120 nanoseconds. So like a kernel system call might be on the order of tens or 50 nanoseconds, so we add 100 something to that. And the key thing is that some of them have a little bit more overhead than others. In particular, for example, you see mmap 500 nanoseconds. That's because, again, we have to do some in-engine work. We might have to decide, is this some mapping that we're doing? There's some things that we don't allow you to do, so there's some checking that you shouldn't do every mmap call ever. Same for something like pread. That's because there's like stuff that we have to adapt, like one of these structs. So basically, whenever there's engine work, that's when the overhead is more. Otherwise, it's really just go through. And you notice there's one glaring outlier, which is clone. So that's the Linux system call for make me a new lightweight process. That's how Linux threads work. You get a new process which happens to share all of your virtual memory mappings, so it's effectively a process that has all the same memory, and that's how Linux threads work underneath. So in addition to that work, we have this instance per thread model, and so that means the engine actually has to go and make a new copy. So that's effectively all the WAMR overhead for making a new instance. So WAMR is not as optimized as WASM time, so it's not quite as cheap as WASM time. So that's like, let me multiply that out. That is actually milliseconds, so that's like 5 milliseconds. So that's a lot, and hopefully that could get a lot smaller with some of the optimizations that, for example, WASM time does. But notice other things too. So fork works. You can just fork your process. You can exec your process, so you can just like launch another thing. So like, again, think about how bash works. It forks and execs some native executable. You can actually do that in WALI, and so that will work. This lower left-hand corner here is the runtime breakdown of some applications. So this is the overhead, like the sort of intrinsic overhead to one call, and this is like the aggregate overhead. So for Lua is a language that you mostly spend time running user code in the interpreter, and so correspondingly you almost never spend time in the kernel. So there's almost no overhead to using WALI. It's like literally 0.1%. If you're running bash, you spend a lot of time in the kernel, but you don't spend a lot of time going through the adaptation in WALI. So that's only like 1% overhead. SQLite, it's a database, spends a lot of time in the kernel doing lots of page mapping and stuff like that. It's a database, so they do a lot of this copy on write type of stuff. Again, like you're only getting in and out through these small overheads. So there's not a lot of overhead here. So you almost don't measure time in WALI at all. We also measure the overhead of doing a polling for asynchronous signal handling. So that's again to support things like your window changes or stuff like that. These numbers are probably can be brought down a little bit too. So here we actually modified WAMR's compiler to inject a little bit of code into every loop header, and so that's on the order of like single-digit percentages there. Okay, so when we wrote the WALI paper, so we have a WALI paper on archive, and we were not entirely sure what we should compare it to. And so we had these different ideas. We came up with the idea of like, let's compare it to different virtualization technologies, even though they may be in slightly different categories. In particular, we compared to Docker. So Docker is effectively a container solution where you run processes natively, but then there's like interception of system calls in a similar kind of way. And then we also compared to running on QEMU, which is an emulator. It gives you the portability guarantees. So the idea is that we're comparing the portability guarantees that you might get from doing ISA virtualization a different way, and the virtualization of system calls that you get from doing it natively. And the results are kind of interesting. For one, Docker takes a lot more memory than we thought. You can be a little bit smarter about how you build Docker images to get that down, but the default one is actually pretty heavyweight, so it spends a bit more memory overhead. Docker also imposed, so if we look at break down the results a little bit more. So this is the execution time. So 3 different applications, Bash, Lua, and SQLite. What we see is that, so this is if we make the program do more work, so the native execution time, so increasing the load of an application, and then this is the corresponding execution time on whatever virtualization it is. So this dotted line is like if you ran the native executable, that's 1-to-1. So anything above that is going to be overhead. So if we look at Docker, which is this orange line here, there's some offset, so there's like some startup cost to Docker, even though it mostly traces native execution time for Bash. Obviously, an emulator, ISA emulator, even though QEMU does have a JIT compiler and all that in it, it's actually pretty slow, so that's why this goes up like this. Of course, it has like effectively no startup cost. And so the blue line is actually WALI, and so there's effectively no startup cost because we use WAMR in AOT mode. But there's this like region here, for example, where you actually run better than Docker because you avoid the startup time. And similarly too, like there's always this region where WALI is kind of better. We're not really selling this as a performance thing. It's more of a layering thing. But this is part of our due diligence as engineers to figure out what the overheads are. Are there questions about those performance results? So there's like lots of things going on there. Okay, so that's like the technical details. So you can kind of see it's quite predictable when you start with the idea of making it 1-to-1 system calls. You crank through the work of it and you measure it. What is actually the future of this afterwards? What are the benefits and opportunities and risks? So I see a lot of benefits to the WASM ecosystem. I see a lot of benefits to WASI in particular. So in particular, WASI needs to eventually be implemented. It needs to hit the bottom. So any API which gives you a new capability in WASI has to make its way into the engine. As it is today, that can only be done in the engine because the engine is the only thing that has privileges to do it. And my dream is that eventually you have a WASI implementation that is against the OS interface, so WALI in this case, and then it's not per engine, and so you don't have to do engine work if you're doing WASI work. So if you introduce new capabilities, you can write that in a language, compile it to WASM, and it will run against WALI, and then now it runs where every WALI engine is. WASI has some implementation state, so it introduces new kinds of security mechanisms. It has capability-based security, it has some additional sandboxing, and it has new concepts. All that is some state that's associated with the user application that's using WASI, and that now can be a WASM module, because we can move it up so we can separate WASI applications from each other and also from the engine. We got fault isolation. So programs have bugs, WASI implementations may have bugs, so what happens when they do have a bug? And that means that we can isolate the fault from the WASI implementation from being able to take over the engine. In terms of specification, we're going to eventually need to talk about what every WASI API does, what its semantics are. We can have a reference implementation against an OS interface, compile it to WASM, and now we can reuse sort of the executable semantics of WASM and say it's this WASM program executing against this operating system API. And hopefully, in the end, we can also verify WASI applications. So we can use the properties that you get proving things about WASM programs and WASM engines, but also prove that about the WASI implementation itself. So that little library that implements WASI, maybe we can actually prove that it's correct. So just to give that an illustration here, so in the world before we had WALI, the WASI implementation would live inside this WASM engine. And so it could potentially have bugs in it. In the new world, that lives inside of a WASM module. It's a WASM sandbox thing. And so, you know, my amazing art skills here. So if we have a bug here, an out-of-bounds write, for example, which could happen because not all of them are implemented in wonderful, safe, memory-safe languages, that means that you could compromise the entire WASM engine, which means that you can take over the entire process. And so you could do anything that this engine could do, including talking to the kernel. Now you can start attacking the system, right? Whereas in this world, if there's an out-of-bounds memory write, you get the memory sandbox of WASM backing you up, so you can only access the state which is in that module, and therefore you could start attacking the engine, but you can only attack the engine with the things that what are the capabilities that have been given to this module, which should be smaller than the entire WALI set. So I'm an engine person primarily, so I think about this from my perspective. There's lots of benefits to WASM engines. So we reduced the trusted computing base. So all of the system interfaces, those no longer need to be, anything that uses system interface can be moved up and outside of the engine. This gives the engine a more clearly defined role. So we need, I think that Luke ran over a little bit. We have a break next, is that right? We are into the break. Okay, I'll try to speed up a little bit. So engines now have a clearly defined role. So they validate and execute code. They're for composing and sandboxing modules. They give you debugging tools and introspection. And then they give you this thin operating system interface. And that's like the end of their job, right? So they don't implement a new security model. They don't give you new I/O abstractions. You can do that yourself above. And I demonstrated the fault isolation. And this also helps engines develop faster because they have a clearly defined role. So engine experts, compiler people, they don't have to go spend time working on system APIs. And they can run more things. Once they have the system API, they know that they can run modules because they're a layer above. Applications that are out there, well, what is the portability benefit, or what's the benefit to them? They get portability, so you don't have to think about a native CPU when you compile your Linux application. Maybe in the future, Linux packages actually come as WASM by default, so you can compile away your source language, and then you produce this binary package, and the code inside is WASM. For security, there's some really important processes that run. For example, SSHD, and there's like lots of other system things. It makes sense to me that you could have them be WASM or WALI processes, and so they could never ever, by design, have a remote code injection attack. There was a really comical one recently with SSH agent. Obviously, SSH agent is not the kind of thing that you want to be able to have any executable writable pages of memory, but there was an exploit change where they managed to load several shared memory DLLs in a row and unload them, and they were like kind of in a partially initialized state. So they exploited the dynamic linker to be able to get writable executable memory, and then they did a remote code injection attack on that. So even though people know about this, we're in 2023, now we're in 2024, that was last year, there's still exploits like this. So I think that like WASM is sandboxing technology. We can just completely eliminate that. It's more lightweight than a full process because you can have a little WASM module that runs against WALI, and it doesn't need like libc and all the other stuff that drags in. And of course, WASM is not the world's best development platform as it is today, but eventually it'll get better, and as it gets better, it means that all of these Linux applications, they will get access to all the WASM tools, so fuzzers and race detection and all that. I think it'll be better for the ecosystem, so we can WASM even more things, so more targets, meaning more collaboration and investment, so we're no longer just a niche technology. And we can build WASM applications in Linux directly. So again, our research partners, they like WASI and they like the component model, but in the brass tacks, like they're still building Linux applications directly. We can run more things on more engines. We can access functionality which has not yet been figured out how to put into a WASI API. And it also means that WASI APIs that are envisioned now, they become available more soon, because they can run more engines, because there's an implementation against the WALI, for example. And it's a stable target, which is something that we've heard from some of our partners, that they're a little bit scared by the evolution of WASI, and they don't know how they would use it or justify to their ancient upper management what it means that a WASI API is still evolving, standard yet. It benefits programming languages. They get sharp knives. That's, if people have seen the paper, we have sharp knives in the title. That's what we're referring to. It means that a programming language that targets WASM gets to do all the things. They don't have to rely on the native libraries, assembly or libc, to do that, and they can directly target the powerful capabilities, and they get all the WASM level tools. Research community benefits because all of their research is higher impact. The bigger the ecosystem, the more impact it is. Eventually, this whole tower, we can start thinking about attaching proofs to all of these things. Will it run the web? I don't think so. I don't think it will run WALI on the web. And, well, is Linux going to now be the only thing ever? I don't think that's true either. I think that we could maybe have operating system interfaces for other key kernels as well. That's pretty much the end of it.
So we are now a bit into the break. If anyone has any questions, please put up your hands. Great.
Thanks. A very brief question about portability. I maintain a JavaScript engine, and we frequently get requests for implementing a syscall API in there, which we don't do. Instead, we're going for an FFI thing, mainly because of portability. And the main problem there is that Windows doesn't have a syscall API that is specified in any way. There is no public documentation of these syscalls or any stability guarantees. Do you see any future? You mentioned Windows as one of the platforms where you could have such an API. Do you have any approach for that?
I thought about this. It's a similar but not quite as bad situation on macOS too. They have a stable kernel API. They change rarely, and they kind of recommend that you link against libc. I think Windows is a similar situation. You're recommended to link against DLLs that have a more stable API, and they might do that for security reasons. So it may be that an operating system interface isn't the exact syscall thing, which might change. So whatever operating system vendor, they get to decide what level of stable interface that they offer. So you would want to pick something that they are committed to already maintaining as a stable interface.
Okay, makes sense.